Good evening, everyone. We'll just wait for a few minutes, or I guess for another minute for everybody to join. My name is Amin Medani. Got the honor of chairing this webinar. Let's just wait for another 30 seconds or so for people to start joining in. We're expecting a pretty large group of participants today, so. All right, let's do that again. Hi, everyone. Good evening or good afternoon, wherever you're joining us. Welcome to a really special event today. This is a bit different. Usually these webinars are catered around the topic that's more clinical focused. We have the honor of doing something kind of different surrounding artificial intelligence in surgical education, which is a really cool, interesting topic, cutting edge, a new technology and innovation, and it's really exciting to chair this session. Before we kind of dive into the actual topic, I'm just going to show a few slides, just describe SAGES, which is our organization. So let's get started. So those of you, I don't know if everybody here is a member or how you kind of got a chance to hear about this webinar, but SAGES is a Society of American Gastrointestinal and Endoscopic Surgeons. This is part of the SAGES family. I do want to encourage everybody to, especially the trainees that are joining us, to become a member. There's a lot of benefits from becoming a member, even as a trainee. I certainly became a member early on in my residency, and the amount of networking and collaboration that I've been doing since then has been quite dramatic, thanks to joining this organization. A lot of my closest friends that were now staff are friends that I met at this organization as well. There's a lot of benefits to being a member of SAGES. Number one, you get a discount to join the annual meeting, which is always great. There's also it's a little bit different SAGES than a lot of some of the other societies that we tend to attend. There's a lot of cutting edge, a lot of innovative, like new things that they tend to present at the meeting, and not just at the meeting, but also available online as webinars, courses, for instance, like robotics courses, online learning material, and so on. So there's quite a lot of that. Like I said, networking is a big thing at SAGES. You get access to thousands of colleagues, and you get to run into a lot of the people who are program directors and really leaders in their field. So it's really, really great. Obviously, there's the social media pages that you can join. You get subscription to surgical endoscopy. There's a lot of grant opportunities as well, career development awards. I can tell you I've benefited from that quite a bit throughout my training and also as an early faculty. And there's a lot of different leadership opportunities. And I can tell you right now, one of the great things about this organization is you can be as early in your training. If you have a lot of motivation and enthusiasm, the leadership is really keen to take people like that into committees and task forces, and it's really based on meritocracy in many ways. So do get involved if you're interested in a lot of that work. These are, this is the vision and mission and values of the organization. And the thing that I really like about SAGES is not so much because it's MIS. I'm not even an MIS surgeon. I'm an endocrine surgeon. I do MIS, but anyways, I don't consider myself an MIS surgeon. But the area that I really love about this organization is it does a lot in terms of innovation and using new advances in technology and really pushing the boundaries. And it also does a lot in education as well, which is something you don't see too much in a lot of other places. You can join, there's different categories of membership. the residents and trainees, that's usually as a candidate membership. It's very easy to do, and it's very, very cheap as well. And usually the institutions will help to subsidize that. As medical students, you can also become members as well. So that's kind of my plug for the Society of American Gastrointestinal Endoscopic Surgeons. And there you have a link if you want to become a member. Okay, back to the topic. So today we're going to be talking about artificial intelligence in surgical education. It's kind of hard to not go through social media, Twitter, wherever you go, and not have to hear about something in the world of AI and that's permeated our everyday lives. And obviously, a lot of that has started spilling into healthcare and surgery. And there's a lot that we can learn and apply and to do better in how we treat patients. I am super excited about the panel today. And I'll tell you why, because typically when we do these sessions at SAGES or wherever, they tend to be a lot of, it's only general surgeons usually, but we selectively took people who are not general surgeons other than myself. We've got urologists, neurosurgeons, thoracic surgeons, really kind of leading the way in their own, pioneering the field. And we've got really an amazing lineup of people. Really, this is like the who's who of like surgical AI. So we'll start off. A lot of these topics are very new, like AI, computer vision, machine learning, deep neural networks. Like there's a lot of terminology there. And I think the first sort of 20 minutes, I'm going to kind of spend time just describing what those terms are, just kind of very high level introduction. Just to provide some kind of introductory, term to some of these advanced terminology, so that it can really set the stage to really fully embrace and understand what the other speakers are going to talk about. Then we're going to go into Dr. Andrew Hung, who's just a world-class urologist out of California, who's really done so much in the field, and he's going to talk about using AI for assessment and feedback. And then we've got Dr. Ruchi Tanawala, who's a thoracic surgeon. I want to say Ohio, or Oregon. I'm so sorry, it's skipping my mind. You're going to have to tell us later. But anyways, she's going to talk to us. She does a lot with informatics, and she's going to talk to us about AI to augment operative performance in terms of what the current state is and what are some of the emerging methodologies in this field. And then finally, we're going to dive into Dr. Daniel Donahoe, who's a surgeon based out of Washington, DC, not Washington State. He's a neurosurgeon who's done a tremendous amount of work as well. Excuse me. He was also done a lot of work in this field, especially in neurosurgery. And he leads a lot in building international collaborations and infrastructure to enable capabilities in surgical AI, really some foundational work in the field. And he's going to be talking about, how do you develop, how do you validate an algorithm? What are some of the best practices to do that? So, we wanted to provide you with a really good overview of some of these topics, so you can walk out of here with some, some practical things as well, so you can know where this field is going and how you can incorporate that into your everyday life. We're going to do Q&A as well, a few minutes after each talk and at the very end. Okay, let's get into it. I'm going to give you an overview of, AI, machine learning, computer vision, surgical data science, a lot of those terminologies. You hear these words a lot, and it's important to kind of provide some definitions. These are my disclosures. I'm not going to talk about any of them or selling you anything. So just to introduce myself, my name is Dr. Madani. I'm a general surgeon, endocrine surgeon, I should say, out of Toronto, at the University of Toronto, and this hospital called University Health Network. This is my hospital, and this is my lab. It's located in this place called the Michener Institute, which is part of that. And Toronto is really great. They have a really big hub of biomedical innovation, and there's a big AI sort of community there. And we work with a group called the Vector Institute, which is basically a large sort of academic consortium of data scientists that are there that we collaborate with. in my lab is basically this multidisciplinary team of people, surgeons, AI scientists, engineers, game developers, and so on. And we kind of come together and basically design technological solutions around needs in surgical education to improve performance of surgeons. That's kind of like what I do. And my background is really not like, I'm not an engineer or computer science or anything. My background is purely in surgical education, understanding what makes an expert surgeon. So a lot of qualitative research, a lot of understanding what decision making is, things like that. And I got involved in this field after meeting some smart computer scientists who allowed me to translate what I've learned about the clinical applications of improving surgeon performance and safety and quality of surgery. And we collaborate sort of with people all over the world, different subspecialties and so on. So that's me, and just kind of my background. So, okay, so what is AI? AI is the study of computer science algorithms that give machines the ability to act, to think, to perform things on a high rational level, sort of like humans or suprahuman, perform things like cognitive functions or perceptual functions. This was previously thought to be the stuff of science fiction, but there's really been an explosion of these advancements and methodologies and applications. And obviously the late press is filled with them. AI can write articles for you. This one was done by GPT-3, and now there's a new version of ChatGPT and large language models. You must have heard this in the news at some point, which perform natural language processing, the ability for algorithms to create human language and natural text. So in this case, it can write an article, but it can also write, poems for you, for instance. Or in this case, I asked it to write a song in the style of Taylor Swift on surgical AI. So you can ask it to do quite a lot of creative things. And students at school and universities are using it to write essays. Researchers are using it to write manuscripts. Journal editors are going crazy because nobody knows if you consider ChatGPT to be a co-author. So it's a new thing and it's kind of changing. It's a big game changer. This has really changed the programming world. There's this joke about how the new programming language is English, because all you need to do is tell ChatGPT to write your program to do this, this, and this, and it'll write the code for you. So there's quite a lot of applications and new things it could do. You must have heard about deep fakes before. You can record a video, apply a filter, and it makes it look like a celebrity or Mona Lisa is talking. And this technology has become very scary good. You can now apply someone else's voice on those videos as well. This is an example of Leonardo DiCaprio. So I hope you heard that. But yeah, this just kind of give you a taste of what AI can do, which is quite scary. AI has been used for computer vision, which I'll talk about in a bit, and generative AI. And this has completely changed the creative industry, graphic designers, music production. AI can create music in the voice of somebody, of a popular artist. So it can do animations, all sorts of really, things that really traditionally took a long time to do. AI can also create art. What's more human than art, right? And this isn't just kind of random, abstract, art anymore. It's actually, you can give it a prompt and it will generate what you want. Like, this is one of my fellows who said painting of a hernia repair in the style of Picasso, and it'll kind of do that. It looks pretty cool. Or an astronaut riding a horse. So it can do a lot of, very deliberate things as well. So AI has inevitably spilled into healthcare, and surgery really stands to gain from this explosion in information technology. Radiology has really, I think, been the most impacted. Also pathology, cardiology, neurology. I think surgery has kind of lagged a little bit behind. just because of the nature of the work that we do. Perhaps our data is a little bit more challenging sometimes to work with, but it's catching up, and there's quite a lot that we can learn there. So that's AI. Okay, so what's machine learning? Machine learning is not the same as AI. Machine learning is a subset of AI, and it's really the current boom in AI. I think is largely, if not exclusively, focused on machine learning techniques. What is machine learning? So machine learning is about building computer programs that can extrapolate from data. So if you think about traditional computer program, you program it very explicitly with a desired behavior. So when you do this, this happens. When this happens, that happens, and you program all of that in detail for all of those scenarios. Machine learning is a bit different. It allows a program to learn by recognizing patterns in the data. So you give it a whole bunch of examples, and eventually it learns from that. And then it goes on to make predictions on new and similar data that it has never seen before. So it's not explicitly programmed for every possible scenario. It's a pattern recognition thing. And deep learning, deep neural networks is a class of algorithms that have made machine learning so successful. So deep learning is not the same as machine learning, which is not the same as AI. They're kind of subsets of each other. There's various forms of machine learning. So training an algorithm to recognize patterns, there's different ways. The most popular one is probably something called supervised learning. This is the idea that, okay, I'm going to train an algorithm. Well, I'm going to give it hundreds of thousands of examples so that it can figure out how to do that on its own. So you take a data set, and then you have to tell it. So for this scenario, this is what the outcome is. For this scenario, this is the outcome. For that scenario, this is the outcome. And you do that hundreds of thousands of times. And eventually, so that's what's called annotating a data set. And then you give that annotated data set to the algorithm so that it can train on that data. And eventually you end up with a trained model. And so then it has new data that it has never seen before. It is able to make predictions. So that's this very simplistic way of something called supervised learning. There's also a form of something called semi-supervised learning, where you can train a preliminary algorithm, and then that algorithm then annotates on more data so that it becomes smarter on its own. So there's subsets of these things as well. Unsupervised learning is another class of machine learning. Basically, the idea is that, okay, here's a bunch of data, figure out patterns that make sense. So this would be something like in, for instance, e-commerce or Netflix or all these websites like Amazon, where they can kind of cluster you into a specific group of people. Like, okay, Dr. Madani, who's 37 years old, lives in Canada. These are all the purchases he had made in the last month. I can make a prediction that he's in this category. People can predict that this is what he's going to want to buy next. So it's able to kind of provide very user-centric information like that. So that's how a lot of examples of unsupervised learning algorithms. Reinforcement learning is another form. This is actually a really cool form of machine learning. It's basically the closest we have to human learning. Is basically the idea is like, okay, AI, I want you to learn this objective. So I'm going to put you in this simulated environment where you can do trial and error again and again and again until you become better and better at doing this particular task. That's what reinforcement learning kind of is. A really good example of this is, I don't know if anybody remembers this, but Atari Breakout, this was sort of like a paddle and ball and you got to hit the bricks. So Google DeepMind developed this reinforcement learning algorithm where they put it in a simulated environment so it could learn how to play the game. And its objective is to optimize its score. The AI knows nothing about a ball, a paddle, a bricks, paddle of bricks or anything like that. It just needs to know that it needs to optimize the score. So after 10 minutes of training, it's not doing very well. Cool thing is, after 2 hours of training again and again, it eventually figures out what patterns will give it this optimized score. And you can see it's starting to play the game pretty well, probably better than I can. But it becomes really scary though, is after 4 hours, it not only becomes really good at playing the game, but it becomes very creative at really knowing how to optimize its score, like getting the balls into a corner so that it could really make the score as high as possible. So this is where reinforcement learning can be really cool. And one day, things like robotic surgery, automation of tasks in the operating room will start to, I think, incorporate these kinds of algorithms. Deep learning, we talked about deep neural networks. This is sort of a class of algorithms that have really become popular and that have allowed machine learning to become so powerful. They are especially good for things like computer vision, recognizing data on pixelated data. The way they work is they're very similar to your, the biological nervous system, where you have an input set layer, you have intermediate neurons that modulate the data, and then you have an output. So for example, let's say we have a neural network that we're training to predict what kind of animal is in the picture. So every single pixel of that is a input data. And then you've got intermediate neurons in there. So basically these are able to recognize different shapes, like the shape of the beak, the texture, this corner and that corner, high level features. So in this algorithm, it can say, okay, based on this pattern of feathers, this pattern of the beak, and this color and that color, I can predict that this is 95% probability of bird based on all the data that I've been trained on. So that's kind of what a deep neural network is. It's just a very complex algorithm. One of the main applications of AI, especially where deep neural networks have been very popular, is with computer vision. The ability for algorithms to understand what is seen or what is happening in images, videos, or pixelated data. And so it's able to kind of cluster those pixels and extract high-level features like corners and textures and things like that. And it's able to achieve high-level recognition, like human level, object tracking, scene recognition. So one thing it can do is classify the frame as a whole. So it can say, okay, in this picture, there's a koala. But it can go further. It can say, not only is there a koala, but this is where the koala is. You can do all sorts of things like object tracking, for a variety of different applications, like tracking, whether or not, a boxer has been punched or not, and tracking score or where someone's been punched and so on. So the applications can get quite creative. This person went viral after they developed an algorithm that basically for sign language, that translates sign language essentially. So there's a lot of cool things. There's algorithms that will track this is me on my own camera on my laptop. It can track all my joints in my fingers and provide all that data. So really cool stuff you can do in vision. You can also design algorithms that can make predictions on individual pixels. So what is the probability that each of those pixels is in the object that you're trying to recognize? So it'll not only give you like that box, but also delineate the object for you. That's something called semantic segmentation. And ultimately, how does this apply to surgery? Well, if you think about how these algorithms, like this is Tesla's self-driving car AI, it's able to see the world. It's able to tell you this car is going there, that car is going there. There's a stop sign. This is where you drive. This is where you don't drive. Eventually, we want to be able to do that in the operating field to track things and provide us with useful information. But ultimately, it's important to recognize what ML is good for. ML is really useful for identifying subtle patterns in very, very large data sets, very unstructured data, patterns that are very, may not be, that are probably imperceptible to humans by using that, more, techniques like complex nonlinear relationships, compared to conventional statistic analysis. It's really a pattern recognition tool. Like this animation will sort of illustrate. It doesn't understand the larger context of a problem. It's just for pattern recognition. And this is an algorithm that you type a text and it says, okay, create a salmon in a river. And this is what it'll produce for you. Obviously, it doesn't know that, yeah, sure, these are salmon in a river, but you didn't mean a fillet of salmon. You meant like an actual fish. So it doesn't understand these kinds of things. Its performance is highly subject to also how it was trained, the source data, how it was curated and fed into the model. So in other words, garbage in, garbage out. And now that takes us to surgical data science. How can AI and things like that be used for surgery? So surgical data science is not the same as AI. It's basically, data science is the ability to take data and use it so that we can improve surgical care. The way I like to view AI machine learning, I view it more as a methodology to enable that. So think about, so data science is, basically taking this vast amount of data, organizing it, analyzing it, creating prediction models, with it, and to allowing us to help us care for patients, ultimately help everything from quality, safety, resource management, things like that. And when I say data, surgical data, I mean everything from vitals, labs, images, pixels on a video, and so on. All the information the nurses type in the computer during a case, that's all data. Today's practice, think about it, there's a wealth of data on each patient. However, it's still up to us as individual surgical teams. We integrate all this data, we take all our domain experience and knowledge to integrate this and figure out what we want to do for a patient. Like, we kind of have a gestalt based on how a patient's information is and what we need to do for them. Fast forward to the future, we want to be able to tap into modern computational techniques like AI to be able to integrate this avalanche of data and find patterns that we cannot see as humans and augment our abilities. So kind of like this seamless integration of computational support tools in DOR, tools that will augment our abilities, make us superhuman, and so on. And it's this kind of data-driven augmentation of surgical care. It can be anything from improving your decision support during a surgery, or perioperative decision making, or algorithms that can tell you what your performance is or what you can do better. Track your performance over time. You can picture yourself in the OR of the future and AI saying, hey, based on the vital signs of lab, the tissue perfusion, the pixels, I can tell you that this anastomosis is going to fail. So you should change your tactic. That's kind of what we mean by data-driven augmentation. And when I say data, this is what I mean. Like, you can have demographics, disease data, diagnoses, labs, vitals. You can have intraoperative data. Andrew Hung, who's going to talk to us, has done a lot on kinematics data with the robot. All of that data can be used to make prediction models, for whatever application there is. And deep neural networks are extremely data hungry. You need tons of data to train an algorithm to make good, robust predictions. And Daniel Donahoe will talk more about that in terms of validation at the end. How do we bring AI in the OR? There's quite a lot. It's a broad field. There's many applications. You can use it for quality improvement, for intraoperative real-time guidance, resource management, obviously surgical education, perioperative care, also autonomous surgery. So there's quite a lot of applications. In surgical education, it's important because, well, surgical performance is it's quite a heterogeneous thing. But if you look at data, surgical complications are quite a lot. Adverse events happen quite a bit, regardless of what subspecialty you are or what part of the world you're in. And you look at the root cause of adverse events in the operating room, most of them are somehow related to something that happened in the operating room that's preventable. And usually the root cause is something like a lapse in judgment or error in decision-making. So if we can improve what we do in our performance, if we can give people better feedback, coaching, things like that, then we can really improve patient care. Think about pilots going into a cockpit. They don't just kind of go there and fly the plane like we do with surgery. They usually have an entire navigation system about them. And that's kind of what we do. AI can be used to provide you with intraoperative guidance. For those of you who know the critical view of safety, our general surgeons here, algorithms that can tell you whether or not critical view of safety has been achieved, and things of that nature. AI can be used for performance assessment, and I'm not going to go into detail about that because other people will, smarter than me, will talk more about this, but algorithms that can track your instruments, the kinematics of your instruments, the motion, path, curvature, velocity, and make sense of your performance level. One of the things we've done at our institution is used AI to be able to provide video review and feedback, so people can upload their videos and they can get feedback in terms of where it was safe to dissect during lap chole. This is something we presented at SAGES recently. Suffice it to say that most people who use this really perceive value as a coaching tool as well. Again, I'm not going to talk about this because someone will talk about this, but we talked about deep fakes. AI can be used to generate simulation models and work out of Germany that can use it to create deep fake surgeries as well. Imagine a world where you can rehearse operations. There's also a lot of challenges to surgical AI and all the stuff that I've talked about. And we can't possibly cover everything, but everything from model development to deployment. So we don't actually have good metrics, in the for surgical AI, a lot, especially in computer vision. We don't have good ways of assessing whether or not our algorithms are doing what we want it to do. There's actually a consortium called Metrics Reloaded, out of the Matrix, Matrix Reloaded, that's looking at all the deficiencies in our metrics. And I kid you not, the next consortium is called Metrics Revolutions. Those of you who know Matrix will recognize that. I may or may not come up with that name, but anyways, the idea is this consortium to develop new clinically relevant metrics that actually measure the clinical value of that algorithm, which right now is just a mathematical equation that just tells you what the mathematical benchmark is, which is not really useful as surgeons. You need data that has trained, on adequate breadth of data. It's generalizable. Models lack a lot of explainability as well. Deep neural networks are good at predicting, but they're not very good at telling you how it arrived at those decisions. And, for all the hype and all the billions of dollars that have been thrown into AI and computer vision and so on, there's actually a lack of evidence and clinical outcomes to suggest things actually improve what we do. In fact, there's almost none. The only thing I can think of is colonoscopy, and even that is like, marginal at best. If we want to train an AI to be able to do something like how expert surgeons would do, you have to understand how those experts think. And so one of the key things is you want to design an AI algorithm, you have to understand what the clinical need is, the unmet need. You have to design an algorithm that's really going to be high yield. So this is where qualitative research is important, doing cognitive task analyses. So this is for adrenalectomy, something I do. We've mapped out all the different things that expert surgeons do. And the important thing is to map out, where do errors occur? Okay, errors happen in this area right here of the operation. And so design your algorithm to, provide you with support with that step of the operation. So it's really important to kind of do that needs assessment. Just like any innovation, unless you kind of understand the unmet need and design your technology around it, it's bound to not really be successful. There's a lot of issues with ethics, regulatory approval, IP, patient privacy issues. These are all big topics on their own that I'm not going to go into, but suffice it to say they are major problems. Data acquisition, like I said, deep neural networks are data hungry. So we don't really have good infrastructure to bring data from all over the world together. And there's a limited availability of experts to train AI algorithms. So that's a big obstacle. This is me in the OR. This is the first time we deployed an AI algorithm live in the operating room for decision support. It took a long step to do that because a lot of the algorithms that you have out there are not generalizable. We had to develop something that was applicable for regardless of what your laparoscopic tower in the OR is. It has to be able to take that image and be able to make predictions on that. It's got to be computationally not heavy, so that you don't need big, heavy equipment in the OR. You can just bring your laptop and actually get that data. So you have to be able to scale it to, especially to places that are low resource, that may not have the capability to bring big machinery in the OR. So we build a data pipeline that allows us to do that. And also, for the interest of time, I'm not going to go in all the detail, but suffice it to say that you can literally be anywhere in the world and take your mobile phone or your laptop or your tablet, capture a video or a screenshot even on a monitor, and it'll take it to the cloud and give you a real-time interpretation. Just like my lab coordinator is doing there. There's a video of a lab chole and it's using your tablet to get real-time guidance. So that's kind of one of our missions, to make surgical AI scalable. There's a lot of design issues that go into it. How do people want to perceive the data? As people want to know the confidence level of the algorithm. So you have to be able to adjust for that. Some people want a model that'll only tell them, like in this case, where the goes on the safe area of dissection is only when its probability is very high. So you can actually modulate your model to do that. This concept called human in the loop. So you don't just blindly do whatever the AI takes. You actually cater it to what you want to do in the OR. And ultimately, we need to build a digital ecosystem for surgical data science. A lot of us on this call, whether it's through SAGES or the Surgical Data Science Collective or the Global Surgical AI Collaborative. A lot of us are putting work into creating a digital ecosystem where a lot of that data can come together to create these algorithms that we can then disseminate all over the world. So in summary, AI can perform many perceptual and cognitive functions. Machine learning techniques are very powerful tools for improving surgical care, but there are many obstacles. And ultimately, if we can tap into this technology, we can improve quality, safety, stewardship, resource optimization, provide better and more equitable care. With that, I'm going to end. And okay, and we're going to start, I guess, our first Q&A. Let me just do my screen share. I would ask all the other panelists to come online, and we'll tackle these questions. Okay, so I see I have no sound in my video. Okay, sorry about that. Basically, it was Leonardo DiCaprio talking and different people whose voices were put on his, as if they were talking. So, okay, I've got a question from Ryan Berry. Even if we identify the skills and tests of skill to better educate surgical residents through AI, we will still encounter historical skepticism of a skill-based assessment. What practical measures can we take to affect cultural reception of skill-based assessment? There are many initiatives related to skill-based medical education efforts facilitated by AI, but I do not know that the larger community is ready to embrace the technology. What have you learned about how to change, thought behind the typical conference and the publication outlets? I think that's a really great question. It's like so on point. We were just talking about cultural change, and I think it starts at conferences. It starts at outlets like places like SAGES, where people have a sort of that mindset of doing things better and differently. It starts at in publishing about it and talking about it, and I think it's just a slow process that and you kind of chip away at it little by little until the culture starts to change. I think the other thing is we have to celebrate our wins. I think we have to sort of promote work that's been done by our collaborators. So every time I give a talk, I try to kind of give examples from different people that are doing different work, that's interesting. And I think we need to actually show value. In the end of the day, you have to show that this is improving performance. You have to show that this is actually, and I think Andrew is probably going to talk more about this, but there's at least 24 papers out there that show that you can use AI to objectively and reproducibly measure skill performance. So if you can show that kind of value or improving patient outcomes through a real-time, navigation, if you can provide that kind of value, I think that's where you're going to push the needle forward. But I'd love to hear what some of the other panelists have to say. Anybody?
I'm happy to hop in to contribute to this. Just as Amin mentioned, it's a really important question, because why do we build all these things if it isn't for acceptance, adoption, implementation, and use? And I think one of the key things is, as Amin pointed out, is paralleling our human process. And I think that's where we get buy-in. Like, if there's this black box around how does this algorithm, how does this technology understand how we're going to assess someone in assessment, we've all been trainees. It's a really personal thing, because we sink our heart and soul in training. And I think if we show that we're paralleling how we actually learn, how our educators teach us, there's going to be better adoption. And I think it is education on both sides, and it's a willingness on those of us and others who are developing these technologies and these processes to actually let everyone know and say, it's actually built off of how we actually learn, and we're layering all these other advantages on top of it. But the foundation is a human-driven, human learning process.
Totally agree with that. Andrew, you seem to want to say something as well.
I'll touch on it a little bit in my talk, but I think that the common perception is that AI is opaque and really a black box where something goes in and something else comes out, but you don't want to ask questions, or you can ask questions, but you can't get any answers in what happens in the middle. And it's really up to the folks who are, doing the studies in here in the space to leave a paper trail so that folks really can have as much transparency as possible. And in that process, get the buy-in, get the trust, and show the credibility. And so I think it's, the responsibility of many folks to prove and to show that it is trustworthy and it is run by humans, and there is a process there, that it's not a magic wand that you wave and suddenly you have this magic that happens on the other end. So it's really the responsibility of the community, of folks like us and others, of course, to make it believable.
Such a good point. One of the key things here, I think, is building trust. A lot of people I've spoken to, especially when we want to deploy this, talk about, well, can I really trust it? Is it really better? And there's all this question of what's its probability prediction on this and that, and having sort of a transparency around that process, I think, is key. Daniel, you want to throw one more comment in there before we move on to the next question?
Yeah, I mean, just briefly, I mean, I can't help but feeling like we're in about baseball in about the late 1970s, and we're coming up on a Bill James statistical abstract 1981 moment here. There's always resistance, and especially in our community, and frankly, there should be resistance, right? We're a community of expert practitioners, and we care very much about what we do. If there wasn't resistance, we'd be in the wrong room talking to the wrong people. So I don't think that that's a challenge. I think it's just a question of recasting and making sure we're all aligned on our ultimate aim, which is getting the best outcome for the patient, and making sure that the systems that we're putting in the operating room actually achieve that end. And once you see that tide change, I think very, very rapidly attitudes. I think that's the one thing you can take away from the last 7 months of AI, which is a huge hype cycle, but the societal attitudes towards AI can change on a month-to-month basis and really profoundly shift. And I think that's all based on user interaction, user experience, a phenomenon, not based on underlying technologies. GPTs have been around for years, actually, and the fundamental systems for a decade even. So I think that this seems unchangeable now. And I think in a short amount of time, we'll actually look back on this and be amazed that it didn't change sooner.
Thanks for mentioning that. Although I don't know if was that a baseball analogy, because I don't think I understood that.
Baseball, yeah.
Completely over my head. Okay, well, just quickly, Dr. Crongrover, good to see you or hear from you. Your question talks more about methodology. I want to leave that to Dr. Donohue's talk at the end of the session. I think he's probably going to touch on a lot of that question. I think Garrett Skinner asked, in your experience, how excited are engineers and non-physician researchers to work on surgical computer vision? Did you or others have trouble finding technical collaborators? I'll say absolutely not. They are dying for usable data that they can do stuff with. And I think they're sick and tired of the usual data sets in non-healthcare fields that are, I feel like there's some kind of excitement when I go to my technical collaborators and I'm like, I've got these videos. This is going to help improve, surgeries. And they're like, that's so cool. I want to do it. Like suddenly it's like a use case that's so exciting for them. So I have not had problems. There are so many smart data scientists, engineers, collaborators that on the technical end can provide a lot of collaborations. And I know some of the people on this call, you work with some of the world-class experts in AI around the world. And I imagine you all have not had problems finding technical collaborators. On a show of hand, anybody have problems? No, right. Yeah, it's I would say it's pretty easy. So depending on your institution, it might be a good idea to kind of reach out to who's kind of, in your department, your institution. If you don't know who, feel free to reach out. There's always somebody who, is looking for collaboration in this field as a computer scientist. And then there's a few other questions, maybe just for the interest of time. we'll just continue with the talks, and we'll save these talks and get back to them. You know, I'm sure we're going to find a way to answer them some way, shape, or form during the session. So with that, I'm going to introduce our next speaker, Dr. Andrew Hung. So while you're sharing your screen, Andrew, so Dr. Hung is a surgeon scientist who specializes in robotic surgery, urology, kidneys, prostate. You know, Dr. Hung, he's actually one of the world's experts in this area. And if you follow surgical AI research, every month in Nature, NPJ, you know, there's digital medicine, there's always a new article by his team of collaborators. And so we're really excited to have him here. He started off at Yale, went to Cornell, then did his urology residency at USC, and then did some advanced fellowship there. And he's been staff at USC for 9 years. And now he's transitioning to Cedars-Sinai in July, where he's the vice chair of academic development there. He's really internationally recognized as a leader in assessment and simulation, especially with robotic surgery. He's received industry grants and the NIH. And he's really done a lot of work, especially on automated performance metrics, like I said, in robotic surgery. He has collaborations with USC and Caltech, and he actually works with one of the leaders in AI, who's one of the sort of in charge of AI and NVIDIA. And so he's got very strong collaborations there at Caltech. And so anyways, I'm going to leave it to him and talk to us about surgical assessment and feedback. Andrew, take it away, please.
I mean, it's great to, it's very humbling getting an intro from you, and fantastic talk, and thank you for having me. So I'm going to speak in a rather narrow lane of surgical assessment and some words on feedback. This is my disclosure, and the work that I will share with you in large part is funded through 2 R01 grants through the National Cancer Institute. So my talk overview, mostly on surgical assessment and a few words on surgical feedback, and we'll go from there. So for the last decade or so, my team has looked at quantifying surgeon performance in various aspects, and hoping that I will cover prime examples in each of these spaces. The first of which is kinematics, motion tracking. A lot of my work has been in the robot-assisted arena, and so that has lended nicely to being able to track where the surgeon instruments have been. Also touch on technical skills as well as surgical gestures, and I'll explain a little bit more detail what those mean. So first in kinematics, so this was a partnership with Intuitive Surgical. This particular grant was a 5-year multi-institutional study where we recorded surgical video through this black box. And in addition to the video, we had synchronized systems data. And this data included instrument tracking, as well as what we call system events. And from this data is what we then derived what we coined as automated performance metrics. So I'll give you a few examples. One could be the velocity, distance traveled, acceleration of instruments. Some of the more complex ones had to do with the angulation or the changes of angulation, radians changed of the instruments during suturing. System events included camera use. Every time the camera pedal was adjusted, that was counted as a system event. And so that's really what automated performance metrics were. And we published this in the Journal of Urology, and this was the first time where we had, in this particular case, an illustrative example of what an expert surgeon looked like during an operation. This is the bladder mobilization, the very first basic step of doing a prostatectomy. The red is the tip of the right-hand instrument, the green is the left-hand instrument, and the black is the tip of the endoscope. And here is an expert having done this same operation thousands of times, and you have a novice surgeon who has not done it thousands of times and really trying to accomplish the same exact task. What we realized in that particular study, or in the inception of this project, was suddenly we had a ton of information. We had at 30 hertz data that was refreshing where the instruments were in 3D space. And then we derived these automated performance metrics. And the question was, well, does all this data matter? We can collect it, but does it matter? And we have so much of it. How are we possibly able to process through it? And so we thought of machine learning as a natural space to parse through this information. So in our very first study, and this was published in JAMA Surgery, we looked at 70 consecutive robot-assisted radical prostatectomies. In every case, we recorded this library of automated performance metrics, as we showed you previously. And for each set of these metrics, we had a clinical label. And early in our experience, the clinical label that we had readily available was the length of stay, hospital length of stay after surgery. Most patients after surgery stayed for 1 or 2 days, and very few, but still some stayed over 2 days. So for these 70 odd cases, we had these automated performance metrics. We tagged them with this clinical label, and we trained a machine learning model. And so now with the trained model, we had a brand new case just finished in the operating room. We have this set of automated performance metrics, and we wanted to predict how long was this patient going to stay in the hospital for. And again, this was very early in our experience. To our surprise, with only these automated performance metrics, nothing about the patient, we were able to predict with the 85% accuracy whether the patient was going to have a 1 or 2 hospital length of stay or more than 2 days. The concept of automated performance metrics we've published in multiple issues of the Journal of Urology, and in fact, they were kind enough to allow us to have them on the cover as the feature cover art. And so it spoke to the interest of these metrics in projecting outcomes and so forth, but there was a ceiling of how much information they could provide. And we thought that, and certainly there was a limitation that in able to anticipate outcomes, and without going into other studies, and for the interest of time, there was a ceiling. And the frustration was that while it told us everything that happened on the instrument side, it didn't really give us much information of what was happening to tissue. In surgery, it's about the instruments and its engagement with tissue. And so there came technical skills. So this is one of the follow-up studies to the one that I showed you earlier, still with prostatectomies. I'm sorry, I'm a surgeon. I'm a urologist, I should say. And here, looking at prostatectomies, one of the key outcomes after surgery is urinary continence recovery. Most patients after prostatectomy will have some degree of incontinence, and that's regained over the course of weeks to months, sometimes years. And we know that for this particular outcome, there is a combination of patient factors and surgeon factors that may contribute to when these patients may recover function. So in this particular study, we looked at 16 patient factors, such as their age, their body mass index, the severity of their prostate cancer. And we also looked at certain factors, which included some of these automated performance metrics, which I shared with you previously. But here we also added technical skills evaluation. And this is an example of what that entailed. So in suturing, this is using the race metric. There are different aspects of how well a surgeon sutures in the reconstructive part of the operation after a prostate's been removed. So how well they hold the needle, what's the angle of that needle entering tissue, how well is the surgeon driving that needle through and rotating their wrist atraumatically, how well are the sutures placed, et cetera. And long story short, if you look at just automated performance metrics, as I alluded to earlier, the ability or the accuracy of this model to predict when these patients would recover urinary continence was somewhere in the 60s, and not great. If you add on technical skills, so the first time in our team where we looked at that tissue, tool to tissue engagement, we finally were able to break about 10 points higher. And again, the ability of these models to predict a patient outcome that happens weeks to months after surgery. And if you use this combination of automated performance metrics and the technical skills assessment, we were able to get our performance scores into the 80s. And that's still to date one of the best models that we have trained. Because it is a machine learning model, in addition to predicting or anticipating, let's say, a patient outcome, we're able to also generate a feature rank. And this is looking at the 400 some odd features or different aspects that the models is able to look at to accurately or not accurately predict the outcome, we queried for the top couple. And you see here, this is the top, 15 or 20 of these features that allowed the models to correctly predict when these patients were going to recover their urinary control. And as you see, the red is, that's the only patient factor. It's not the only patient factor that we looked at, but it's the only patient factor that was listed in the top 20. And things to do with technical skill of the surgeon ranked very high up. And it was because of this sort of work, and this was many years ago now, I would say about 6 years ago, that it really, got my mind thinking that, if we had the opportunity to get NIH funding, we really want to look at surgical skill. And so this is the first of my 2 RON grants through the NCI, and Anima Anand Kumar is my collaborator on the machine learning side. And notably, Anima is not only the Bren professor at Caltech, but she's also the senior AI scientist at NVIDIA, and most recently, she's on the I believe the Science Council at the White House. So in another JAMA surgery paper, we outlined our vision of what we wanted to do with this particular grant. We wanted to take surgical video. Now, this could be from the live arena, or it could be from virtual reality. And we wanted to take these videos to train a model to do a 360 assessment of surgeon suturing skills. So this is an 18-point assessment of all the nitty-gritty aspects of suturing, and we wanted to automate this process. So all you would have to do is show the video to these models, and it would spit out on the other end these skill assessment scores. And further, from our the prior work that I just showed you, we know that there's a relationship between technical skill and patient outcome. We want to then have a secondary model that can then project if this were a patient, whether in VR, there's obviously no real patient, but if this were, let's say, in live surgery, if these are the skill set that a surgeon exhibits, what would be the projected outcome for that patient? More recently, we've had 3 papers come out in the Nature family, looking at this surgical AI system that we have created that, amongst many different things, can do skills assessment. And so that's our centerpiece paper. Then we wanted to make sure that these assessments are fair, and further that they are explainable. And this touches on what the prior question that we were addressing earlier. So very briefly into each of those 3 papers. This is the centerpiece that is in Nature Biomedical Engineering, looking at this surgical AI system that we developed, where we take surgical video, and through the complexities of these neural networks, at the end of it, we want to provide an assessment for very granular skills, such as how well is the surgeon holding the needle? How well is that needle being driven through the tissue? So for different aspects or different skill sets, we are relying on different pipelines having significant commonalities between them, but we are outputting very granular skills assessment. And if you take an original data set, it was trained with USC surgeons. We also tested on a holdout set of other surgeons that were not part of that training set. And we want to see that the model, continues to perform well. We also want to see that if you've trained this data on surgeons from USC, that if you now test it on surgeons from a different hospital, this is from San Antonius in Germany, that the model performs equally well, or at least is comparable. And finally, the ultimate test is that if you have a model that can do a certain task in, let's say, a prostatectomy, and more specifically, the nerve spare part of a prostatectomy, but it's about tissue dissection. Tissue dissection happens in many different operations, including for us as a urologist, kidney operations. Well, if it's tissue dissection and it's recognizing behavior there, we want to see that it performs equally well in recognizing these surgical gestures in a different procedure. And in fact, we see that there's a drop off in performance, but nonetheless, the model still holds up. It's important that models are fair. And if it's in high stakes, such as assessing the quality of a surgeon, we want to be sure that the model does not have any bias. But unfortunately, if you naively train these models, we saw that the models in fact do exhibit bias. For instance, between more experienced surgeons and less experienced surgeons. In our training center, we found that the models perform differently for male medical students versus female medical students. And so one is recognizing that there is a problem there, but secondly, adjusting that or mitigating this bias is absolutely important. And so we've taken the steps of not only seeing that the bias exists, but also taking steps to mitigating this bias. And one way of mitigating that bias is, in fact, looking at where humans look to assess the quality of a surgeon. So if you had, let's say, 1,000 frames of surgical video, a human trained evaluator doesn't have to look at every single frame to make an assessment, a fair and objective assessment. They are looking at very specific aspects of surgery, depending on what the skill is. Here you see in yellow where the surgeon is in fact looking at these 1,200 frames of video. The blue is, if we ask the models, well, you've made an assessment, which parts of the video are you looking at? You see that there is some overlap, but there's not perfect overlap. And what we found was if you train the models to not only see the ground truth labels, or in other words, we've provided these models what a human expert rater would provide as a good skill or a poor skill labels, that in addition to that, if you provided these models where the human surgeons are looking to make these assessments, that in fact helps the models perform better and actually helps to mitigate some of the biases that we saw earlier. Okay, so that's a bit on technical skills and just very briefly on surgical gestures. So our team has tried to break down surgery into the smallest elements of what surgery is. And these are the very small moment-to-moment, second-to-second maneuvers. So as you see here, these are some of the blunt dissection gestures of spreading tissue, pushing tissue, hooking, making a single cold cut, an energy cut, and what we call burn dissect, pulling tissue towards you as you are coagulating. And there's also more complex combination gestures as pediclize, a two-hand spread, and then coagulating tissue and then cutting it. So if you go with this particular scheme or classification of surgical movements, you can actually take surgical video and decode it to the sequence of surgery. So where you may have, similar to the genetic code, have spread, hook, burn, peel, etc. So this is some of our more contemporary work with the second ROM grant that we have, looking at the nerve spare set of the prostatectomy. So what you see here is 22 rows, and each row is the first 100 dissection gestures, and they're color-coded to the gestures I just shared with you. And what's similar about these 22 rows or 22 cases are, these are patients, 22 patients who had erectile function sufficient for sexual intercourse before surgery, but 12 months after surgery do not regain that function. In contrast, these are 18 additional rows or 18 nerve spare steps where the patients did have function before surgery and recovered that function after surgery. So if you think about it, historically, this is an operation, this is a very critical step of the operation, the nerve spare step, where we've had all sorts of ideas of what may be good and not good for erectile function recovery. But the truth is nobody really knew, because from the time of surgery, it would be months, if not years, or at least a year, to have some semblance of outcome. And so that's been the challenge. What we found was that if you took proportions and if you take the obvious things like energy usage, et cetera, that those things are not great predictors of outcome as we would have anticipated. But if you plug these sequences into sequential models where there is a memory of one gesture after the other, and you remember the orderings of these gestures, these models can actually predict with an accuracy somewhere in the 70s to 80s whether or not the patients will recover function a year after surgery. And, this was such a groundbreaking outcome for me that I didn't quite believe in it. I, in fact, had both our Caltech team as well as our USC machine learning teams duplicate the work, well, using the same data and same mission, and to ensure that, in fact, we were arriving at that common conclusion. And in fact, yes, they're not the highest performing models, but they point in the similar direction that, yes, in fact, these sequences are telling us something. What's going to be more important in this space is that we are not only able to anticipate or predict that outcome, but really identifying where are the critical areas where, if you do these particular gestures or do them in this particular order in certain places, that you are protective, you're positively impacting their erectile function recovery. And conversely, are there areas that are increasing risk that the patients will not recover function? And of course, these are the things that would have to be avoided. And like I referred to earlier, this is the subject of our second grant. So the first grant was on suturing and automating the skills assessment in suturing. Our second is on, to us, the ultimate tissue dissection, which is the nerve-sparing part of the prostatectomy. So finally, in just the last few moments, I want to share with you. So we have spent about a decade on assessing surgeons and quantifying them in our hopes the most objective way. We're nowhere near that finish line, but that will be a continual journey. We've shifted, or we've put some of our attention on feedback. So once you have the perfect assessment of a surgeon, you got to come up with some delivery vehicle and being able to deliver that feedback back to the surgeon, and therefore then hopefully improving their performance. We're just beginning in that journey, and I'm going to share with you a paper that's going to be coming out very shortly. And I can't tell you where it's under embargo, but the concept is, if you take surgical feedback in the live operating room, there's typically a trigger, something that the surgeon or the trainee has done correctly or incorrectly. They either did something incorrectly, or maybe they didn't do something they should have done. That elicits the feedback itself from the training surgeon. And then there's some kind of response, ideally a positive response on the other end, once person has received that feedback. So we've looked at 30-odd robotic prostatectomy or robotic cases that we're teaching cases, and we have gone through this whole process where we've identified 3,700 lines of feedback. And we've tried to categorize what the triggers are. Again, errors of omission, errors of commission. They've done something that they shouldn't have done. We've looked at the feedback. The feedback could be could be categorized as to is it feedback about anatomy, where something is, a structure, important structure, procedural, what they should be doing at this particular juncture, or technical feedback. They're doing something technically incorrect. They're not rotating that wrist as they're driving that needle through tissue. And then there's some ancillary parts of the feedback. Are they providing a visual aid to help, convey their message, for instance? And then what's the response? Well, and this is our first, drive in all of this. The response could be that the trainee clearly changes their behavior. It could be that the trainee at least verbally acknowledges that they did something wrong. They understands the feedback, et cetera. So this is the very beginnings of some of this work. Well, what's the utility of this classification system for surgical feedback? Well, we've looked at different areas. So if you look at, and I think this is for one very specific instance. So if the training surgeon is providing anatomic feedback, whether or not they couple it with praise or not, makes a difference in terms of the trainee exhibiting the behavior of verbally acknowledging, the feedback. And so, this kind of work may allow us to train our trainers a little bit better in saying that, hey, if you deliver feedback by itself, if you couple it with something else, maybe, you can make your feedback more optimal. I'm going to stop there. There's not much of AI yet in that particular realm. You can use your imagination of where that could potentially take us, but I'm happy to take any questions, or maybe we move on to the next talk. Thanks for your time.
Thank you so much for that, Andrew. Fantastic talk. Just the idea that we actually have evidence that AI algorithms can predict outcomes predict events. I mean, it's just something that's a big. These are the type of things that I think are shifting the needle and shifting the culture. So congratulations on all your groundbreaking work. It's quite remarkable, to be honest. Maybe I'll start off a question while we wait for anybody who has any very specific questions for you. A lot of your work that you've done is very specific to the robot, where you can collect a lot of that kinematic data. For a lot of us, not in California, we don't have the robots, or at my institution we have like 1 or 2 robots, and everybody's kind of wants that OR time with it. But suffice it to say, most people don't have access to a advanced platform like that. How do you see these kinds of algorithms scaling, especially to places that don't have this kind of equipment? Just kind of want to hear your thoughts about that. The second question I have for you is, do you think it's enough to understand or really evaluate someone's performance based on a video alone? A lot of the research in performance, suggests that a lot, like the high advanced cognitive behaviors, the mental processes, those are really the thing that really define an expert surgeon. The ability to become creative in weird situations, the ability to figure their way out in something really tough, or troubleshoot and become adaptive, and those kinds of high level things, as opposed to more very granular technical pieces. Do you find, like, what's the next step to kind of extract that kind of information? I just want to hear your thoughts.
Thanks, Amin. So to address your first question, I think, in robotics, it's almost a cop-out. It's easier because the video is stable and you always have relatively good vantage points. Not to say that this could not be applied elsewhere. So I think if you can get the basics down in a scenario where you have good vision, then you tackle open surgery or surgeries where you just have a lot less space and maybe not always optimal lighting. And so it's hopefully this is foundational to a lot of work. And in fact, when we convinced the NIH to fund us, that was part of it, is that, hey, we recognize that this is a problem that the root of which is not for old men with prostate cancer and all that kind of stuff. We're really trying to solve something that's more broad and general. To address your second question, absolutely, there's in addition to what the surgeon's explicitly doing, he or she, we've also looked at biometrics. So we've looked at heart rate variability. We've looked at the pupillary changes as measures of cognitive workload. And we think, that space, there's a lot more noise, but, being able to look at other processes, and the challenge is finding a space where you have a lot of control over the environment. But unfortunately, things that are even, the biometrics space there's so much, it's just really messy. And maybe you need something like ML to parse out through the noise to really hone in on areas. And we've done some exciting work in that space too. And I know many others have as well. So absolutely, this is a small sliver of what you can look at from a surgeon, from the surgeon perspective, but there's many more.
Thank you for that. I might go to one of the questions, and then we'll leave the rest for the end, just for the interest of time. Somebody asked Kevin Chan asked a really interesting question. Really impressive work. Development of robotic surgical skill assessment based on kinematic data seems to be limited to partnerships with Intuitive, and your more recent work seems to be more vision based. Do you see vision-based skill assessment becoming more prevalent in the future because of this? And any thought on improving access to kinematic data? How do we improve collaboration, especially when we're working with companies that can restrict our access to this kind of data set?
Yeah. So hopefully there are not a lot of Intuitive folks on this particular webinar, but it was a very intentional move from kinematics, which, out of all fairness, is proprietary in many regards. And it's not just Intuitive, it's many of these folks, guard their this kind of data. And so it was a very intentional move that if we move to video, and videos by all means you should not be restricted to just robotics, laparoscopy, and even open if you can get the right equipment, hardware, that's accessible to the masses, and it's easy. You don't need special equipment to record in the operating room. So that was a very intentional move on our end, that the work we want to do, we want to touch as many folks as possible and not be restricted to folks who have these special, agreements with whichever industry partner you have. And so, I would say that that's not likely to change anytime in the future, the kinematic data. What we've actually been looking at is to see if we have both, and we still have these special partnerships where we have both kinematic data as well as video based assessments. Can we come up with some kind of translation between, or some dictionary that converts one to the other, so that you still may have the advantages? We essentially would create this synthetic kinematic set of data, even though you don't really have it in all instances. So that's something that we're working towards.
Thanks for that. All right, I suggest we move on just out of interest of time. I'm going to introduce our next speaker, Dr. Rishi Tenawala. Thank you for joining us. I know that she was in the OR, scrubbed, and sometimes clinical work obviously takes precedence, but we are grateful that she's able to join us. I'll just introduce you again. My mistake for as a non-American. Ohio versus Oregon, sometimes I get mixed that up, but I'll just kind of mention that she was recruited in Oregon Health and Science University about 3 years ago. She's a thoracic surgeon, assistant professor there. Now she completed her cardiothoracic surgery fellowship at the University of Iowa, did her general surgery training at the University of Massachusetts Medical School, Bay State Medical Center. And she's a practicing thoracic surgeon who does a lot of MIS, really the comprehensive care there. Basically, her work is really in the gap of applying data science and informatics in our drive to kind of do a lot of that competency-based surgical education and skill assessment. She did a Master of Science in Health Informatics in Northwestern University, and also did the SURF Fellowship in the ASC. Those of you who don't know, the American Association of Surgical Education has a fellowship program called Surgical Education Research Fellowship, which is a really great opportunity if you like this kind of work. But anyways, she did that, and her work brings together the fields of informatics, focus on data science, AI, surgical education, clinical surgery. And her niche is really informatics-driven surgical education, integrating AI and surgeon computer-based workflow optimization. And she's done a lot of work on a national level, developed a platform that she's going to talk about as well. So with that, I'm gonna let you take it away. The title of her talk is AI to Augment Operative Performance, Current State and Emerging Technologies. Dr. Tenawala, please take it away.
Thank you. So thank you all for an opportunity to be part of this wonderful and esteemed panel, and thank you for that introduction. Surgical education is near and dear to my heart, with my research, and I'm 2.5 years out of training. So I finished my fellowship not too long ago, and I often still think of myself as a trainee as I'm in this, learning phase, still in becoming an independent thoracic surgeon. So for disclosures, I'm co-founder of Firefly Lab, and I own stock in the entity, and I've received no compensation for it. Okay, so AI, as Amin mentioned, really broad term, a term that is used, thrown around a lot. AI meets surgical education, and the angle that I've taken to this topic is kind of a high level with a couple of drops into kind of the details, but really at a high level, because what is operative skill? And that's a really complex skill. I have a slide dedicated to what is actually operative skill and performance. So I think we can all agree that artificial intelligence adds new dimensions to how we learn. What it is not a magic solution. It is not going to replace our current learning paradigms. Our learning paradigms, the way that we train and the way that we're taught, the way we progress through our careers in gathering knowledge and improving, so gaining skill, maintaining skill, mitigating skill loss, is based on a really established process. And that is still a human to human knowledge transfer that, as you know, when we were talking about a previous question, is being augmented by these technologies. But artificial intelligence, machine learning, all of these things are not going to replace how we learn. What it is doing is adding in all these other dimensions that we've never really had access to before, or known that it was possible that we could actually amplify the signal and the benefit of those than just being, you know, perhaps noise in the environment. What it is doing is personalized learning. And probably most importantly is actually giving learners more control over how they learn by removing the information on how well you're performing outside of the head of our educators and putting it directly in front of our learners. So questions are, you know, how can artificial intelligence and all of its forms make us better in the operating room? Who can it help the most? Because we all identify that, let's not even think about this at the level of what training you are. Let's think about this of where we are in our phases of learning, like the learning curves. A lot of my research is actually focused on Bayesian modeled learning curves and where we are in our learning of skills such as a specific component of operation, the use of a tool, all the way up to a composite like entire operation. And what aspects of learning is it most helpful in? So we're gonna kind of address those things. I'd like to establish the premise from the outset is operative performance. When we're talking about operative skill and performance, it is a composite skill. So it is not any one of these things, it is all of these things. And this is why when we think about how our technologies that we're talking about today can help in operative performance, it's how it helps from all the different angles. So technical performance of a skill, like the actual dexterity, how our hands do things. Someone had put up a slide, it might have been Amin that actually talked about, you know, what the judgment component is, which is up to like 70–80% compared to the dexterity component. Both are there, both are relevant. There's variable split in the influence of either one. Recognition and avoidance of errors, you know, to actually improve our skill, we must recognize when we might be making an error and avoid them. And as Andrew pointed out, a lot of these machine learning and deep learning algorithms and technologies can really help with that. Judgment. We need to know what we should do and what we shouldn't do. And then there's the cognitive flexibility. I actually find this to be one of the most interesting things. And at the end, I'll talk about some of my own research using machine learning and mapping out technical and judgment flexibility in a trainee's ability to complete an operation from initial objective to the actual conclusion. And then lastly, it's knowledge. So I'm not going to go too much into this because Andrew has actually given us a prime insight into all the amazing work that he is doing. And I'm going to kind of highlight the work of various groups. So when we think about the role of machine learning and technical skill assessment. So technical skill assessment, it has been a lot in the context of our educators assessing our trainees. So operative performance evaluations, you know, clinic performance evaluations. Again, it is what's in, you know, a human's brain and getting it to the individual learner. But what happens when you kind of decouple that? And, you know, some of the challenges are that when we have a human, it's time costly, it's financially costly, and there are variable biases. So we have to kind of sort those out. And I think, you know, one of the participants had asked a question on how do we get people, because there's skepticism about skill assessment. And I think because we recognize there are a lot of these biases and it's hard to get a lot of assessment data. But what humans do have when we are part of the assessment process is this integrative knowledge, the relatability. And we talked about, you know, this learning paradigm. The people that are training us have gone through this exact same learning paradigm. But if we think about the advantages of machine learning, is that if we figure out how to assess technical skill, it's scalable, as Andrew pointed out. It is potentially cheaper labor over time because, you know, you're not waiting on your faculty to have the time to do the assessment or have the conversation with you. The downsides are you need larger training data sets. We usually start in a narrow space and then have to expand it out. There can be biases as well. So this is one study by Lam et al. And this was kind of a high overview. It was a systematic review. And the goal was, can we identify if machine learning tools are adequate assessors of surgical performance? Used a large amount of kinematic data and then use a smaller proportion of video-based data. The machine learning methods were diverse because it was over 60 studies. And as you would expect, each group, used a different mix of studies. But what it did is it spanned general surgery, ENT, urology, and ophthalmology. And they focused on a variety of tasks we know that we trained in doing our FLS testing, other ones like video-based assessment in pig models, laparoscopic, open operations, robotic operations. Without getting into the weeds of the actual study, let's think about the numbers. So the majority of the studies reported about 80% accuracy. So just kind of putting that into context, that's pretty good, but there's some challenges. And as there can always be challenges when you look at these broad reviews, but when we think about how we're going to apply machine learning, to help in technical assessment, it's going to be in a diverse set. So one of the challenges in the data set is that the tasks evaluated were really diverse. Another challenge when we're looking across all these is the classification systems used. So novice versus expert, the use of standardized assessment tools like OSATs. And in one of the studies, they actually looked at patient outcomes. And cross-validation is challenging. So while 80% is not 100%, 80% is really quite good. And I kind of want to bring this back to when I laid out the objectives of how this can help is it can personalize and individualize the learning. So if we have a trainee, self-motivated, as all trainees, we've all been there, and this is why we're doing this, is the methodology is there. If we can put and use machine learning to put advancing skill and performance in the hands of our trainees, then we're making them further independent learners. And we have the technology and ability to do that. Another space in which artificial intelligence, deep learning is helping is actually by improving operative technique and skill by integrating in sensory data. So I think all of us know in the operating room, we don't just use our hands, touch is one of the prime things. Vision is another, those are the key two senses we use to decide if what we're doing is going to work, not going to work, lead to the outcome that we want. But there are other adjunctive things. And probably one of the biggest is sound. Sound isn't when we're using the cautery or when we are, finger fracturing tissue and we can, hear a crunch or we can feel it and then hear it. So I wanted to, as I was looking through all of the work that's currently being done, I found this to be a very interesting work done by Siebold et al. And this was actually using a deep learning based model for acoustic sensing to prevent surgical errors. And this work was actually done in orthopedic surgery. So within thoracic surgery, using drills. I mean, this is also something that's familiar to me, but we can understand how this could extrapolate. The key objective of this study was to limit iatrogenic injury to neighboring structures when drilling through bone. And the data that was used, which I think this is, pretty interesting novel work, is acoustic data. And this experiment was done in cadavers. And what they're looking to identify is that point of bone breakthrough of the distal cortex. So they used a deep residual network architecture, and their results were they're 88% effective in sensitive in detecting breakthrough. So what this tells us is that the noise, the sounds we hear in the OR that we in our brains as human surgeons integrate in to help us identify, is this a normal sound? Is this not a normal sound? Like I'm dividing the airway. This is making different sounds than when I normally divide the airway. Can we actually develop an algorithm or a tool that can help us to know this is normal or not? And again, this is advancing the learning. So these are learned skills that happen with experience in the operating room. And we're talking about how to improve operative skill, how to enhance it, how to augment it. It is shortening the learning curve. And this is a place at which we can shorten the learning curve in integrating acoustic data in the operating room to know if we're on the verge of, having an avoidable surgical error. Another place that we're seeing the use of artificial intelligence, most importantly, computer vision, neural networks, is actually in the modeling of soft tissue. And Andrew touched on this. When we're doing thoracoscopic, endoscopic, robotic surgery, probably more with robotic surgery with the loss of haptic feedback, less so with thoracoscopic and laparoscopic, is understanding the deformation of tissue. This goes back to our visual sense that we're using in the operating room to know, as the light reflects off of the tissue, I'm dissecting out the pulmonary artery, is this the appropriate amount of tension or not? And these are true groups, Zhang et al. And Li et al., that actually have worked on 2 different independent processes to actually look at how we can use tissue deformation models to reduce surgical errors and to help guide someone to know the appropriate and inappropriate forces. And again, the impact, all of these are different ways in which we can advance our trainees in our own individual progression across the learning curve to identify appropriate and inappropriate tensions. And what this again is doing is bringing this knowledge directly to the learner and taking it out of the human educator's brain. And now our human educators actually become a really expert overlay upon these algorithms that have, a high level of validity, sensitivity, specificity, accuracy, but may not be as 100%. And the greater number of tools we have to actually further our learning and not just be, the human that's sitting there and saying, Ruchi, you did a good job today, appropriate tension, but we're getting multiple layers of feedback, is how we're actually getting, to the verge of furthering our learning on a regular basis. This is actually a really interesting piece of work that was done by El-Haj et al. And this was actually the use of deep learning, image-based models to actually predict surgical complexity and complications, and some really fascinating findings. So what they did is they used CT image data, and this was for abdominal wall hernias, to train deep learning models. And what they were looking at was surgical site infections, pulmonary complications, and the ability to predict the surgical complexity defined by the need for a component separation. So if we compare the deep learning models versus the surgeon, for accuracy was 85%, that the deep learning model was accurate. And for complications, it was 77%. And then they actually did the side to side regarding the complexity, and the deep learning model was way better overall than the surgeon in identifying the complexity. And the way that this matters is how we perform in the operating room, and how we improve how good we're going to get is our ability to anticipate complexity, because that directly relates to our preparedness intraoperatively and postoperatively. And this is an example of how a deep learning model was actually better than 6 expert surgeons in identifying if an abdominal wall component separation would actually be necessary. So in the last couple of minutes, I would like to focus and spend a little time on my own research, which this is, one arm of my research is in using machine learning to actually optimize surgical learning. And I'll kind of go through the specifics on this. So I'm interested in how machine learning can actually help us to understand and model deeply how we train and learn. And again, this is paralleling how we think and learn surgery. And I'll kind of go through this. And what this does is this machine learning model, it ties directly to feedback and evaluation data. And again, my work, I develop a lot of learning curves, and I started to layer in surgical process mapping. And the goal has been to create a quantitative model for entrustability. In our American Board of Surgery is rolling out our EPAs. So entrustability has been an important surgical education concept for a long time. And we have been thinking through, how can we actually measure entrustability? We've built out the framework for that. What I'm interested in is, how can you predict entrustability so that with each educational opportunity, we are furthering our learner. So I wanted to look at how we could predict preoperative entrustability across all procedural possibilities. And I'll explain what the procedural possibilities are with some surgical process mapping. So the definition of surgical process mapping, and this can be described multiple different ways, is actually that's a technique of deconstructing complex events into individual processes. And Amin actually give us an example of that, a schematic for some of the adrenalectomies. So say, you know, we have a patient that comes into the emergency department with acute cholecystitis. A whole bunch of work happens. You know, there's a consult, we get imaging, we define that the patient needs an operation. When we book the operation, we say the patient needs a laparoscopic or robotic cholecystectomy, possible open, possible intraoperative cholangiogram, and then we actually get into the operating room. And, you know, we have our faculty and we have our trainee. And we start with an approach. We start with, you know, say if we're doing a laparoscopic cholecystectomy, there's a rate of conversion. So what surgical process mapping is doing is we have an understanding, a mapping of all the possibilities, and we have an overlay of the probabilities of each possibility. So there is a probability of the conversion from laparoscopic to open. Generally, you know, this is the understanding with the probability is actually a learned skill. That's part of our judgment that develops over time that makes us effective and safe surgeons. So what we did is we used about 7,500 operative evaluations that we had within the platform that I had built, over 220 for over 220 residents, over 110 evaluating faculty, 3 general surgery training programs, and I built about 4,000 operative learning curves with Bayesian modeling and long short-term memory deep learning models. So, you know, this is a type of recurrent neural network. They're powerful, they're very data intensive, which is why, you know, we needed a lot of evaluations, and, you know, we're kind of, we have our preliminary data on our models and continue to evolve those. And I like to put this in the context of a colectomy. The reason that I picked a colectomy as one of the ones to study is there are a lot of adjunct procedures that can be tied into a colectomy. So in this schematic, you know, we've got a colectomy, we're going to start that. We go in and we know that we need to take this portion of colon out. We're going to start out laparoscopic. And again, there's an opportunity and a possibility of conversion to open. But the other thing is there is an opportunity or a possibility of the addition of lysis adhesions, a colostomy, and then there's a conclusion to the operation. Now, at the beginning of an operation, we don't necessarily know which pathway it's going to take. Again, we have our probabilities. But for our trainee, we would like to make each one of these opportunities as further advancing in their education as possible. So if we can model their entrustability at the start of an operation based on their key performance, then perhaps we can figure out where we need to push them and advance them the furthest. So this is some of our work in this study where we actually mapped out what the residents' individual learning curves are for each aspect, so each possibility of the surgical process map. So you can see that there's actually a wide spread, which we all recognize in real life. We are going to be more comfortable, more adept at certain methods or approaches by which to do an operation, and certain aspects of operations than others. So this resident is has a high level of autonomy in doing a colostomy and a lysis of adhesions. When we get to a laparoscopic colectomy, she performs better than if she was doing an open colectomy. So now integrate all of this in with a surgical process map. And on the right, you can see a mapping of what is the predicted operative autonomy of this resident for each procedure, and put that all together for the entire operation. And here on the right, we brought it all together with a surgical process map, and you can see that there is a probability distribution. So for this resident, if this operation goes by a laparoscopic colectomy with a lysis of adhesions, she has a high level of being able to complete this with a high degree of independence. If it goes by way of a laparoscopic conversion to open with the lysis of adhesions, that open colectomy is probably going to be more challenging for her. So we can see is that if we're trying to find the key points at which to intervene as a faculty when we're trying to advance our trainees' independence, is while we're moving on laparoscopically, she's probably going to be okay. But greater degree of presence and guidance is probably going to need for the open colectomy. And perhaps that is where we can spend our key time in this very time-limited educational environment that we live in to advance her for the next time she does this operation. And what we can see, this is, you know, across 6 residents, is that there is a wide span of what the learning and predictive operative autonomy rates are for colectomy when we look across the residents. But the key thing is that these curves shift rapidly because residents learn quickly. And how do we advance the learning is by knowing exactly what are those key hit points that we need to get to. But how do we know that unless we actually map it out and then we model it and we have this quick iteration cycle? So that's where I spend a lot of my work. Our entrustability prediction model, our initial model has an accuracy of 77%, or precision, or 72%, or precision has been 77%. And, we had done this initial work across 4 operations, and we're currently in the process of expanding this out, scaling it across 100 plus operations in general surgery and cardiothoracic surgery. So as we think about modeling and trustability, the role of artificial intelligence in improving operative performance, it's liberating data. It is about externalizing a lot of the information that we have so we can put it in front of our learners, but we can also help add in all these dimensions on how we learn, and not to replace how we learn right now, but to really augment it and make it better. So to kind of go through those 5 constructs that I put forth at the beginning, technical performance of a skill, artificial intelligence and machine learning is helping with feedback. It's helping integrate in sensory data like auditory data, helping with our visual integration of information by helping us to understand tissue deformation. It's helping us to recognize and avoid errors, again, by the auditory data, image interpretation, judgment, image interpretation with that deep learning model using CT scan interpretation, flexibility with the surgical process mapping, and helping our learners to understand where they have a lot of capability, where they can be more flexible, and how to advance their learning. And then with knowledge, natural language processing. So thank you for that. And I'll take any questions.
Thank you. Thank you so much, Ruchi, with that really great presentation. It's funny, we were just doing, I was running this course at my institution. It's called Coaching to Coaches. It's like it's a workshop for young faculty to get feedback from, the best teachers at our university on how to become better coaches to our trainees in the operating room. And one of the common things that comes down to is how do you foster a sense of autonomy to our trainees? And it's always a major question for everybody. I love the way you have it mapped out that way. That would be so great to be able to provide that detailed analytic so that as when I want to pass on autonomy on teaching somebody how to do a thyroidectomy, I know how to do that in a very, broken down and very a comprehensive way. So really love your work, quite impressive. We are running behind. I do want to go on to our last speaker, just out of interest of time, and we can drill down some questions at the end if there is still time remaining. So I'm just going to introduce Daniel Donahoe here. If you could start sharing your screen, appreciate it. Dr. Donahoe is an assistant professor of neurosurgery and pediatrics at George Washington University. He's a pediatric neurosurgeon at Children's National Hospital. He runs a lab there where he's NIH funded. And he applies basically computer vision and ML techniques to large surgical data sets. His clinical interests are he does minimally invasive brain tumor surgery. Sounds really tough. And prenatal surgery, as well as surgical performance improvement. My God, it sounds like my thyroids are like a walk in the park compared to what you do. He's also the founder of something called the Surgical Data Science Collective. It's a nonprofit focused research organization creating a transformative infrastructure for surgical data science. So with that, Dr. Donahoe is going to talk to us about model development and validation. From CV to GPTs, how do we develop a model, some methodology, some guidance? Take it away, Dan.
All right, awesome. Thanks so much, Amin. Well, this is an impossible act to follow, so I love the challenge. Briefly, my disclosures, I've funding through an NIH K-23, and I want to credit Andrew for laying the trail that in large part I've followed through a lot of my early career and currently in my second year of practice. I have unvalued equity in .phrase.ai and unvaluable equity in a nonprofit, which is to say no equity whatsoever. It said 20 minutes, but I think we're down to about 14. We're going to explain why AI is impacting our world today. I'll show you one of the worst moments I've had in my surgical career and why it motivated me. We'll train a neural network in real time. So we're going to do a live demo. If that doesn't scare anyone, then you probably haven't spent a lot of time in software. But fortunately, it's not my software. And we're going to dissect both a new GPT paper and a computer vision paper and talk about how those models came to be. Ready? Let's go. So this is what I do all day, every day in my dreams. Actually, it's probably only a couple days a week. This is a typical operating room. It's very familiar to the audience here. There's a lot of displays, a lot of data sources, expert mentors, surgeons in training, and our principal challenge is recognizing the David Foster Wallace, this is water moment. We live in a world of data that's constantly slipping through our fingers, and let's understand why that might be. First, we should think about where we've started. Our methods of learning, as we've talked about in many earlier speakers in this talk with great eloquence, largely have not changed over the prior 100+ years of surgical training. This is a picture from Harvey Cushing's notebooks, which I had the pleasure to read during my fellowship, and they were immediately recognizable to me, both as the way that I was learning and in the methods of our operations. That's a problem. So I've got this toddler. He goes to sleep every night. We have this nanny cam. And one day we started getting these emails in our inbox. It was his sleep dashboard. It showed his sleep efficiency, how long he'd spent asleep. And then we started getting these tips. Here's how to put your toddler to sleep, develop a more consistent bedtime. Make sure you're starting the bedtime routine every night and keep it consistent. So I really want to ask this question fundamentally of why are our babies getting better feedback than our surgeons? And in order to understand how this could possibly be, I want to take it back a little bit, and I'm not going to go through this whole sort of seminal article in detail, but Mark Andreessen of A16Z has this phenomenal work in software that's called Why Software is Eating the World. It outlines a series of confluence of both technological, societal, and technical advances that had brought us in 2011 to the point where we felt that software was running everything. In fact, he said healthcare and education are next up for fundamental software-based transformation. Many people lack the education and skills required to participate. Every company I work with is absolutely starved for talent. And yet, in medicine, almost nothing changed. But slowly, something has started to change. And I think it's important to understand what are the preconditions that didn't allow things to change first, and why did this happen now? So first, we have to consider dichotomous categories of data. The first is a dichotomy between structured and unstructured data. Structured data is a defined format, like key values, databases, as compared to text blobs or messy data, like images or video. Secondly, we have labeled and unlabeled data. Labeled data comes paired with a target value, like the patient survived, that's associated with every observation, or the radiologist report. Most medical data doesn't live in this format, and all of our prior analytic methods like multivariable regression live in the structured labeled data regime. So the fundamental challenge that motivated our world today is how do we use massive quantities of unlabeled, unstructured data to make meaningful impact in the medical domain? We now know they're being swept by this AI tidal wave that's changing our world. So why is that? What's the fundamental innovation? In 2017, Jensen Huang of NVIDIA gave this fundamental address 6 years after the Mark Andreessen piece that said AI is eating software. And I'll propose to you that the fundamental innovation that changed over time was the prevalence of extremely large models run on extremely large quantities of compute that could handle extremely large quantities of unstructured, unlabeled data. Sounds a lot like what we've got in medicine. So here's an example of one of the problems that we face today. This is a surgery that I do a lot. I'm going to do one tomorrow morning, resection of a pituitary tumor. When we're operating in this area, we use an endoscope and tiny instruments. And we're trying to hit this thing in the middle here that's surrounded by these big red things. And it's pretty important for us to hit the target because otherwise, and I'll take you back to my worst moment in the operating room, this can happen. So that's a really bad day. But fortunately, we'd spent the prior 5 or 6 years answering exactly these questions that allowed us to successfully manage this catastrophic complication and get this patient home safely. So we started with a series of investigations about visual data and machine learning models that I'll cover through the rest of this talk. So my charge today is to define how we can develop and validate algorithms. And I think that we have to go through this in a step-by-step fashion that actually starts long before we say the words AI and ML. It starts with what we all know how to do, which is defining use cases. So we have to think about things that are clinically impactful, that we understand, and that we can know if we see a solution when it's presented to us. Then we have to assess the feasibility of actually meeting that use case with our data sources that exist today. We have to collect and understand the data, then initially develop simplistic models, refine the models to meet a use case, and then evaluate more advanced models. And if you think about the prior speakers' talks, they've all followed almost exactly this playbook, which suggests maybe this is how we should do it. So how do we define useful, feasible problems? Well, in the world of surgical performance assessment, we have some phenomenal work that's been done over the last largely 20 years to look at actual video data. And as our prior speakers have attested to, when experts look at video of surgeons operating, they can identify visual signals that are extremely impactful. These visual signals, when experts assign each other these skill ratings, can predict complication rates, including surgical complications, things we really care about, like death, readmission to the hospital, reoperation, return to the emergency department. So in summary, there's a signal in video data that is extremely important, and surgical experts know how to get it. But we have a problem. We don't have very many experts, and we have a lot of video. So let's think about what this study showed for us, just to dissect it up a little bit quickly. They looked at clinician ratings of each other. They established expert performance criteria, and that was essentially their predictive model. They used logistic regression defined based on p-values, using R-squareds for best fit models. And they had validation of this only in the sense that they had real, reliable external endpoints and targets to predict on. But this is not a study that in its initial form was replicated in out of sample or generalized out of sample. So those are important things to think about. We know that this applies within this domain. We don't know if it applies to other domains. So one of the things that we've done in our efforts is to create training courses for managing catastrophic hemorrhages, like the one I unfortunately encountered in that first video. But fortunately, before I had my complication, I trained a couple hundred surgeons and had exactly how to manage them. And what I love about these videos in particular is the simple fact that everyone's smiling. So simulation is a very important and low stress environment in which to practice high stakes maneuvers. But when we're doing simulation and educational activities, I'll make one simple plea for you. Start saving the video, because what that allows you to do is create visual data sets. So I'm a big proponent of open data. This is our video data set that we created from these hundreds of videos of surgeons managing a very rare complication in surgery, but in the simulator, we could reproduce it reliably many, many times per day. We ran this in national meetings, and we published this data with labels for the instruments in an open access fashion. You can go download this today. It's been downloaded, and viewed a few thousand times. And it's the basis of several, not of my work, but of several other grants that are being proposed to NSF and NIH. We published our methods for labeling, and I know there have been a lot of questions about how you efficiently label. I think our methods have come a long way since then. In terms of what we did in dissecting the model development and validation that were used in this, to be honest, we used an off-the-shelf object detection model that was based on a particular machine learning architecture that's pretty primitive, but it was 2018, so you'll have to forgive us for that. The use case was detecting objects. We had ground truth data, which was manual bounding boxes, and we created test statistics, the intersection over union and mean average precision. The intersection over union is if you have a predicted bounding box and then you have some ground truth bounding box, how much do they overlap compared to how much are they different? And the mean average precision refers to, in a multi-class problem, what the precision is of your detector across all of your classes. These are details. I'm just giving you introductions to some of these terms to understand how we could potentially evaluate these models. Again, for validation, looking at my toy pituitary model data set, we'd have to take the image detector that we validated there, expose it to novel data sets. We are publishing another data set in spine and many others. And I'd even recommend that you use this on your own data. Now, we can talk a little bit about data. in this, as far as model training and model validation goes, the general paradigm for model training and model validation as pertaining to data is that we divide up our data into several segments. We might consider a data set of training, and that's the data that the model sees in order to finalize its parameters. Those are the essentially the internal elements of the model that allow it to then eventually generate a prediction. We then, after we pass all of the data through the model one time, that's called an epoch, we'll have a validation data set, and we basically score the data against that, score the model against that. And then you might want to have an external test set. Sometimes these terms are flipped in various literatures, which is an unseen data set used to evaluate the finalized model. For example, you might have 80% of your data used for training. You might hold out some of your data for then use on expressing the actual performance of your model. But what do you do if you don't have a lot of data? And dividing it up this way is quite difficult. Well, this is something you should look for in the method section of various machine learning papers. There's a couple of things that you can do with this, and these are some tips and tricks as far as model development and validation. You can do what's called pre-training, which is when you expose your model to a separate and often unlabeled data set so that its parameters are not random, but they're actually based on patterns that it can see within the data set. You can fine-tune your model, which then means essentially you'll freeze most of the parameters so that they can't change from that initial training, and you're only going to train the last couple bits of the model that are most impactful in your outcome. And that's a way essentially to perform what's called transfer learning, where you take a model that's trained on one data set and you use the knowledge that it's essentially learned from that data set on another potentially completely unrelated data set. And lastly, there's been questions about data augmentation and synthetic data. I think it's a little bit beyond the scope of what I can do in 15 minutes. So what can this look like in another paper? This is an example of something that Dr. Hung talked extensively about, which is the development of automated performance metrics. So we took all of these videos of surgeons trying to manage carotid artery injuries in the simulator. We tracked instrument movements over time, and we extracted features or composite elements from that data itself that were then useful as predictors. And we found that when you know how someone is moving the instruments, that's a far more important predictor of their success or failure at managing a vascular injury or not losing a lot of blood than whether they're an attending or not, or what their name tag says on their white coat. This is stuff that we know that's both intuitive, but also fairly controversial. So again, looking at the model development and validation in this study, we used a penalized regression model, which is a fairly low rent machine learning solution compared to what other people have talked about. We predicted blood loss, and we have some of these performance characteristics. This is something that we really hope to validate on other procedures and other data sets. I'm critiquing my own work just to externalize the fact that there's a long way to go in this field. So let's probably just do the live demo, and then we'll try to wrap it up in a second. But I think the live demo is actually pretty valuable here. This is TensorFlow website, and they have a nice playground here. I strongly recommend that anyone who wants to mess around with neural networks go and check this out. So these are some hyperparameters, which are changeable elements of the machine learning model that the model doesn't actually train on. There's some different data sets you can pick here. Features, which are essentially properties of the data that you can teach the model about before it starts to learn about the data set itself. We can make the model bigger or smaller. We can change the number of hidden layers or layers in between the input and output, and we can change the number of output neurons that we have. So just to give you an example of what this very simplistic model looks like at predicting this ringed concentric circle data set, we can start the training, and it's going. You can see the training loss here, less is more, and then it'll come to some, essentially stopping point here. And let's see how the prediction did. It ran through the data 500 times. That's not very good, right? So this band shows where it thinks the blue dots are, and it shows that it thinks that we're going to have a line in the middle and then an orange area on top and an orange area on bottom. That's nowhere near our concentric circles. So what can we do about this? Well, okay, let's give it some more neurons, right? So let's increase the number of input neurons, and we still need to have a couple output neurons for the classes. So make the model bigger, classic ML thing, run it again, right? Boop, boom, and only 106 times through the data set as compared to 500. Now it's got these fairly decent concentric circles. The reason I just want to kind of introduce you to this, I think it's a nice way to kind of play with the different hyperparameters or adjustable components of the model that are not related to its actual training process. You can change the data sets, you can change your training test splits. There's all of the stuff you can do here to mess around with the model. So I strongly endorse this as a great way to have some fun with machine learning and learn a little bit about how to train and validate these types of neural network models. So let's see how my slow book does it. Coming back to Keynote here. Probably should have sprung for the new Mac chip. So now that we're on our whirlwind tour of machine learning, I'll just ask this one interesting question and then probably take it to the break here. Something that's very interesting for us is how do these algorithms compare to human experts? So we did this probably pretty unfair experiment. We took our 5-minute videos of surgeons managing carotid artery injury, and we only showed the first minute to either neural networks or human experts. And we have some standard ResNet feeding into LSTM architecture that I won't go into right now. But essentially, it's a neural network that has the ability to integrate predictions over time and can also understand the image and tool presence data. And we asked our experts. And what was interesting was the experts almost always agreed. In 79 out of 80 predictions, the experts agreed on what they thought was going to happen. But they were only right about 70% of the time. Now, that sounds good, but remember, 50-50 is chance here. You either get it or you don't. So 70% isn't that much better. Even with this very small data set, with this fairly rudimentary model, we were able to comfortably beat the experts as far as predicting what surgeons were going to go on to succeed or fail, just based on the first minute of managing this horrendous vascular injury. And the last thing I think as an audience of surgeons all knows is these models are far more accurate than surgeons at predicting blood loss. There's no skin in the game. They just look at the data. So the models had a significant advantage over the actual surgeons at predicting the actual blood loss that we measured during these trials. So these are the sort of model development validation questions that we get to. I don't want to, I'm going to skip the small data set and augmentation models and just close with a brief discussion about generative pre-trained transformers or GPTs. As far as how these models work, they carry out what's called next token prediction, meaning if you have a sequence of, for example, letters, they're trained through an extensive process at predicting what the next small sequence of letters should be. They're pre-trained, meaning they use an extensive internet scale amount of prior training data, and they use a particular neural network design called a transformer. So that's where the GPT comes from. There's about 1 million of these things that are available right now. Most of these models are secret, and their performance is highly task specific. What's interesting is a colleague of mine, Eric Orman at NYU, recently fed his institution's entire EMR into a actually fairly small large language model relative to GPT-4, for example, and found that it can answer some of these interesting questions better than clinicians, like how likely is a patient to die in the hospital, how likely are they to get readmitted, just based on the unstructured EMR data. So why does this matter? Again, we started off by saying that the fundamental thing we've been waiting for in healthcare data for so long is things that can, models that can understand extremely large quantities of unstructured and unlabeled data. And some of these large language models are indicating interesting capabilities in these areas. But rather than talking about how we train and validate large language models, which is an entire topic that's actually quite up in the air in the CS world, I think the question we're really asking as clinicians about large language models like GPT, are we really asking about the models themselves, or is the question really about the data? In fact, in these models, they're almost inseparable from the training data themselves because of the way the models are generated from these extremely large internet scale or EMR scale data sets. So when we're trying to understand how to validate these large language models, we're really asking important questions about the training data set itself. And that kind of gets us to this topic of how we validate LLMs, which I think, again, is a little bit beyond the scope and time of this talk. But I'll simply say that these are important to validate on your own institution's data. They're important to think about in terms of actual performance measures from actual physicians. So going back to our sort of cute example of comparing experts against computer vision models to predict surgeon complication management, you would want to know how physicians are performing, and the NYU group did nicely in that regard. Is they asked the physicians whether or not the patients were going to, thought they were going to get readmitted, et cetera. So that's, I think, a strength potentially of their approach. And then we might want to know not just how these compare to a generic physician, but how they compare to our actual performance itself. There's an entire emerging field of how we create and train models in this way that I think is incredibly important and impactful, and something that I just want to footnote as an important area that we should all be thinking about. I think talking a little bit about GPTs is probably already been covered a little bit. There are these benchmarks that exist for GPTs. You might notice that none of these categories and none of these benchmark evaluations have anything to do with medicine. So I think that there's an incredible opportunity to create surgical data leaderboards. And I want to really make this call explicit. We had an editorial recently in one of our neurosurgery publications that got into this a lot. And there's an incredible opportunity for young people to get involved in this field and come up with grand challenges and important questions that no one knows yet how to answer, and to formulate the structures that we will eventually apply larger and more complicated models against. And that would add incredible value to our field. It's our job to become informed AI consumers. It's very difficult to evaluate a lot of these models in a world if we don't routinely publish code and data in the complete computational environment needed to reproduce the figures and the results that we see in these papers. And how do we handle this problem where our users don't have the data because it's private and don't have the computational ability without millions of dollars from AWS or NVIDIA to perform the compute to replicate the model, even if you get their code? And I think highlighting this is important to say, we have to be aware that we may be heading for a major reproducibility problem in healthcare AI, which is something we've seen time and time again. Lastly, when these models make it out into the wild, they are not static. And models that are in production, meaning that are part of the actual clinical care environment, have to be continually evaluated and reevaluated to deal with a lot of these problems that we see in every other field, from the insurance agency to textual-based models. So there's an entire other world that I want to expose you to of production machine learning models and machine learning operations, or MLOps, that is really critical to understand how we use these tools in the real world outside of a research lab. I'm going to skip some of this talk, although I think it's important because I think we're significantly over time. I'll end with this concept of modeling from Goodhart's law, that any observed statistical pattern collapses once pressure is placed upon it for control purposes. So in simpler terms, once you start to measure something, it stops being as valuable as a metric. So I think these are things that should give us a lot of humility in developing these models, should really push us towards open and accessible both computational environments and results publication, so that we can avoid some of these challenges that we've seen in the field over many years. I think I just want to highlight really the last sentence on this slide, which is understanding how humans perform with these models is critically important. How we actually pair up humans with AI is one of the great unanswered questions that is, again, beyond the scope of the negative 5 minutes that we have in this talk. I think that one of the things that I think a lot about is the creation of these global surgical data libraries and fundamental systems and structures. And that's one of the things that's motivated me to create collectives of surgeons who are working towards these problems today. And that's where I spend a lot of my time. So I want to thank you guys a lot for your attention. I'm happy to answer any questions for those 49 brave souls who are still on the chat.
Thank you so much, Daniel. What a fantastic talk. As you mentioned, we are over time. I think, what you mentioned is so important. I think as the field is evolving, it's so new, so we're trying to figure it out as we're going. There's not a lot of gold standards that are already established. I think for instance, like I could think about our lab Coley AI stuff that we're doing. The algorithm looks good on numbers and on paper and mathematical metrics, but when you actually deploy it in the OR, it's a totally different scenario. And there's things that you pick up that may not be clinically as relevant as you initially think. So, or even just how to annotate, how do you annotate? How many frames do you take per video? Do you take sample frames? Like, how do you define like there's so many layers to that. How do you define a gold standard, where if I'm an expert and I'm annotating the ground truth for where to dissect in this field of view is going to be very different from what another expert surgeon is going to say. How do you find consensus? Like, all these questions are things that we've kind of had to work our way through and as this field evolves. So really great talk. I really loved it. I'm going to try to wrap this up actually, because we are over time. The one question I'm going to ask is maybe everybody kind of throw your 2 cents is, a lot of people have asked about how do you get involved? A lot of people are sort of, in their own institutions and they don't have the collaborators. People are, in places outside North America, maybe where there's not a lot of infrastructure or people doing this kind of line of research. So the question to me is what advice do you have for people who want to go into this line of research, and how do they get involved? They're very motivated. How do they learn about it and kind of go from there? So maybe whoever wants to start, just go ahead.
Yeah, I mean, I'll say just very briefly, first of all, play to the strengths of your environment, and find teams to work on. Nobody does this alone. I don't do this alone. I think that all of our panelists have both incredible clinical knowledge and wisdom, and still we all rely on collaborators and large teams of folks to help us in this work. And we would all welcome any of the folks who are on this to reach out afterwards.
Ruchi, what do you think?
Yeah, I think don't be afraid to ask. I know when I started this work, when I was a general surgery resident, there wasn't a lot of knowledge or experience locally, and just email, reach outside of, the bounds of your institution, your environment, your country. Just ask. I think everyone here and everyone that I've ever worked with is super excited to collaborate with anyone at any level.
Andrew?
I would say that in the instance where, I've worked with many folks and it doesn't always work out, just to throw it out there, that don't be discouraged, that, your first partner may not be your partner forever. And certainly do not be discouraged. And it is about finding the right partnerships, and not all of them work out, but eventually, they do, as long as there's perseverance and enthusiasm and interest.
That's fantastic. And maybe I'll just add one last word of wisdom that I think is key. Remember, focus, like Daniel said, focus on your strength. You don't have to be a computer scientist or engineer, or you don't have to know how to do programming. I certainly don't, and I lack the technical strength of a lot of our panelists today on this call. My area was purely in qualitative research, and I understood the use case really well. And so I found collaborators who did the computer science part really well. And together we formed collaborations that way. So don't be discouraged. Like, you can do AI research without being a technical guru. So like you said, Andrew, don't be discouraged. Find like-minded people and collaborate and cross-pollinate. That's really, I think, the key to any innovation. So with that, I want to take the time to thank all our panelists for really, this was an amazing webinar, really, like I said, the who's who of critical data science here. And we're really happy to get people from outside general surgery for once giving talks at SAGES. So thank you for taking the time out of your busy schedules to do that. Thank you for all our participants who took the time to listen in. I apologize if we didn't get to your questions. You have our contact information, and you can get, don't hesitate to reach out if there's anything we can do. And last announcement, there is a survey to fill out. You're going to get it as you close the session. Please take the time to fill it out. It's good for us to get feedback, to know whether or not this was valuable, or if we should continue doing this in the future. And that'll be great. Okay, everyone, have a good night. or afternoon, wherever, or morning, wherever part of the world you are. Good to see you, and all the best.